is a kind of a genius, right? You throw it, this is my coin flips, you give it so many coin flips, but at the end, all you remember, or all you need to remember, are this proportion of heads, right? You're throwing away all this information, but you're keeping the thing that's actually essential. For any downstream task, all you need are this p hat, right? So from that very simple example, there's a much deeper lesson, right? From all this information, all this sensory input, how do we extract what's actually relevant, right? And this is kind of a basic idea in statistics, in deep learning. The idea is that a good model should compress information. A better model compresses information as well as possible. So our first way of learning how to compress huge streams of information are going to be recurrent neural networks and gating. So I think of this as kind of the most elementary possible data processor. So what does this formula mean? Think of H as your running stream of summaries, right? HT is your summary at time t. X are your inputs. So what is this function doing? It's taking your old summary, you give it some input, and now you learn a new summary, right? So now you can take in this infinite stream of inputs, all these XTs, and then you can compress them down to this current summary HT. So if you want to think about it in terms of this coin flipping example, your summaries are your p hat, right? And you're just updating your p hat depending on what coin you've seen. If it's heads, you increment. If it's tails, you go down. And that's all this recurrent unit is doing. So I kind of want to have a running example. And I want something a little bit richer than just coin flips, right? Let's say I want a continuous function, just to say, I want you to understand RNNs are much richer than just coin flips. So what I'm doing here is related. I'm trying to count the number of times this series passes through the gray bar. So I know it's kind of hard to see, but there's like a sine wave here. There's a gray bar, and my summary, which I want to keep track of, are these dots, right? And then it keeps on incrementing every time I pass through that interval. So it's like counting. And then, so the idea is if it's flat for a while, and then it increases a few times, so the summary is just flat for a long time. And then it has, thank you, and then it has a bunch of increments. So in a way, I want it to memorize the count that it's seen so far and not forget it. So in this particular example, it's really easy to come up with an RNN processor for it, right? You can come up with an updating function which increments the count every time you enter the interval. And the insight is actually pretty straightforward. The insight is you know that you have entered the interval if at the current time point you're in the interval, but at the previous time point you weren't, right? The only trick you have to make is that in the form of the RNN processor, you're only allowed to look at the current input, right? You're not allowed to look at the previous input. So what you do is you keep that previous input as a steady, you record what the current value of the input is, and you refer to the previous summary, right? So in the first coordinate, you're just recording the raw values of the input, and since you're allowed to look at the previous summary, you just refer to that previous coordinate in that summary, right? So it's nice. Like I write a two-dimensional summary function, and I've completely captured this thing that I wanted to memorize. And if it seemed like kind of complicated math, you can just do geometrically the same thing, right? So this first coordinate is just counting, am I in the interval or not? And the second coordinate is just incrementing every time I notice that I'm in the interval now, but not previously. Okay. So on the one hand, you should find this really impressive, right? We've taken something that's a global property of the sequence, and we've reduced it down to a series of local operations, right? The global property is the total count of the number of times it's gone through this interval, and then the local operations are kind of every time I see an input, I do some update. So that's a pretty deep idea, actually. On the other hand, you should be sort of disappointed, because this is the deep learning Indaba, and yet I handcrafted my features, right? In deep learning, you never want to handcraft your features. You always want to learn them from scratch, right? So how are we going to learn them, right? It's the same answer as we always have in deep learning. We're going to stack lots of learnable units and hope that the composition approximates some useful complex function. So the picture is kind of the usual. What I was doing before is I was handcrafting these complicated functions for the input to the summary and the summary to the summary. And instead, I'm going to have these very simple functions, but I'm going to stack them up deeply. So now, once you stack it up, it should learn these complex functions. The trade-off is I now need to provide examples, right? I can't handcraft the definition. I need to provide lots of supervised examples so that I can learn the appropriate transformation. Okay, so question 1. In order to implement this idea, we need two things. We need, like in here, we need to know what these simple functions are. And then second, we need to know how we're going to learn those compositions. So what should the simple functions be? It's the usual answer. You'd have a linearity followed by a nonlinearity, right? So here's a linear function of your previous summary. Here's a linear function of your input. And then here's your nonlinearity. And I think about this geometrically. Like, suppose that your h's are two-dimensional, right? So the previous h is the orange dot. What is the next h? I just transform, I get some new updated point, and some new point in 2D. So with this choice of the weights, w weight, u weight, I'm moving this original summary to this new output. Or I move this summary to this, I don't remember, this summary to this output, right? So it's learning kind of a gradient field. It's learning a whole bunch of updates from these previous summaries to these new summaries. And as I change my x's and weights, it changes things. So like, here the weights behave differently depending on how it responds to u, right? And now I can change the input as well, right? So does anyone have idea why is this not changing anything? When I moved the x's, it didn't change anything in my figure.
W is 0.
Yeah, exactly. The weight matrix is 0, so the input doesn't change anything. But if I had changed my w to be not 0, then moving around my x, oh no, yeah. Oh, whoa. Yeah, moving around the x does change things then. Right, okay. Just making sure people are awake. Okay, so now that we have these composable units, we need to provide some sort of supervision. So how do you provide supervision in an RNN? There are actually a lot of different choices. One choice is you take the entire sequence and then you have something that you try to predict. So a canonical example here is, let's say you're trying to predict whether a review is positive or negative. Right? You see the whole, something that someone said about a movie, all the different words, those are the sequence. The output, this is whether it's positive or negative review. Right? It could be input to another, like at each input you can provide a scalar. So that would be like in a language model, right? The goal of a language model is you have the whole sequence seen so far, and your prediction is what is the next word, right? And now at each time point you try to predict what the next word is. And that's all a language model does, right? Or you could have a sequence-to-sequence model. So this is like, I really like the example with the medical summarization in yesterday's keynote, right? So the input sequence would be like a medical report, and then the output sequence is now the sequence of words in that summary, right? So the idea is we're going to provide all these labeled examples and then teach the RNN layers to kind of learn a useful summary function so that it can accomplish this task. Okay, it seems like everything should work, but if you tried it as is, this would not work. And the reason is because of something called vanishing gradients. The intuition for vanishing gradients is if you provide an input at this particular time, then its influence on the outputs gets lower and lower as time passes, because you've made a change at every time point. And even if you're making a very small change over a long period of time, the influence of this input on anything downstream gets very small. So I also like to understand this geometrically. So let's suppose that these are the initial summary functions, right? Then, okay, I pass in one input, I get updated. Let's pass in another input, you keep on getting updated. And let's just do this a whole bunch of times. And what do you notice happening? Okay, what had started off as summaries that were all across this -1 interval square, now they're all collapsing to this small point, right? What's happening is my units are saturating, and the influence of the original point, it almost doesn't matter, right? Because they all end up landing at this ending summary. So you can see this even more directly if, like, I try changing the input, the very first value, and okay, it changes the last summary a little bit, but barely anything, right? So that is the vanishing gradient problem. The first input has almost no influence on these later outputs, so it's very hard to learn anything. Okay, so the idea is we're going to use gating. The idea is if you see some information that's useful, make sure that it doesn't get changed. Guard it from any incoming information that might overwrite it. So I added this figure probably because I was sleep deprived, and in my head I was thinking like, yeah, it's like you have barbarians at the gates. Yeah, exactly. And then the gates are supposed to keep you. Okay. Anyway, yeah, it makes sense. If you get it, then that's cool. So how do you do gating? We're going to talk about an approach called gated recurrent units. So maybe it's easier to start with the picture. So this is kind of our usual updating mechanism. We have old summary, new summary, input coming in. But we're going to add these new parameters. What the parameters are going to do is they're going to control how much this previous h matters and control how much this xt matters, right? And let's look into the math to see exactly how they control things, right? So this zt, what is it doing? It's controlling how much the previous h can influence the current h, right? If zt is 1, right, then this thing is 0. Then it means it's not even looking at the previous ht. Versus if zt is 0, then that means whatever your new summary is actually just copying over that previous summary, right? So that's how you interpret zt. RT is a little bit trickier. The way I think of it is it's controlling kind of the relative importance of x and the previous summary. If r is 0, then the previous summary is not that important in the candidate at all, and it's focusing primarily on the x. But then if r is large, then it's kind of looking evenly at both when it comes up with the candidate. So I have the interpretation, basically what I was just saying, but I want to add, we can see it in the picture as well. So let's say this is, I give it some input and that's the new summary. What happens when you make sure that your first input is still relevant for later on points? How do you choose RT and ZT? Maybe work on this for a minute and a half. Implementing an ordinary RNN. You just add a new linear, input for this HT, right? So that's the idea for a typical sequence-to-sequence model. You train this encoder and this decoder connected in some end-to-end way, and now from these decoded summaries, you can figure out what is the associated word, right? Because think of the embeddings, think of the h's as corresponding to some sort of meaning, right? Once you have the meaning, then it's pretty easy to figure out what that word should be. So, a small cautionary point. I just said that as input to your decoder, you're using the previous target sentence word. But if you had the target sentence words, then you wouldn't need to do translation, right? You would just use those words, but you can fix it relatively easily. What you would do is you would take the decoder values, and from these decoder values, you predict what the associated target sentence word should be. And then you use these predictions as if they're the truth, right? So the diagram is, I don't actually see the true target sequence, but I try to predict it one step at a time. In fact, the closer my predicted sequence is to the true sequence, like that's how I measure success, right? So it's like the distance between these sequences. But the point is, as input to your decoder function, you're going to use, is actually a predicted, a y hat. Okay, so back to this original intuition, right? We are asking a lot out of this final summary HT. This one summary needs to somehow encode everything about the source sequence. And this can get very difficult for very long sequences. It doesn't matter that we have gating. Like, gating helps for sure, but for long sequences, you're not going to be able to capture all the information about this shape. So what do we do instead? Kind of one idea is, let's allow ourselves to look at these previous summaries. Let's not just throw them away, right? But then let's look at them in an intelligent way. Let's not just like throw in all the summaries and concatenate them. That would be a little bit overboard. What they say instead is, let's come up with some sort of mixture of the previous encodings, where the mixture puts high weight on those encodings that are more relevant for the part of the sentence that you're currently decoding. Right, so the idea is, if I'm kind of in the middle, like the 1/3 point of my target sentence, I should probably pay attention to the source encodings that are in the 1/3 area. Because you think that the meanings are probably about the same at the beginning of the source sentence and at the end of the source sentence, or at the beginning of the source sentence and the beginning of the target sentence. Okay. So I think here I'm just giving you the formula. The only difference is, instead of capital HT, I have this weighted combination of all the previous encodings. Okay. And the point is, as I step along my decoding, I can now change my attention distribution. I had been paying attention to these points, now I'm paying attention to these points. Right? So that's what this diagram is here. So it still has high weight in the parts of the sentence that are kind of similar location because they have similar meaning, but it again has high weights near the end because it's returned to somewhere with similar meaning. And I just wanted to throw in a little bit more formal equations just so that you don't think I'm making up pictures and saying like, oh, this is how attention works. Like the actual, all you would do, you do some softmax combination either of just the decoding or of kind of the alignment between the decoding and all the encodings, right? So the one that doesn't look at the encodings at all, that's the location-based, right? It doesn't need to look at similarity in any way. The one which needs to look at similarity, that's going to have all these H's, right? Okay, and in case you prefer the pseudocode, it's relatively simple pseudocode. Okay, I think I'm going to skip this exercise. Maybe you come back to it at the end, but just for the sake of time. The solutions are at the end, in case you care. Okay, our next kind of big idea. So if the first big idea of gating was that we should somehow preserve, or we should change the way inputs come in so that we can preserve information for a long time. That was the first big idea. The second big idea for soft attention was we should have some way of navigating our encodings so that we don't force ourselves to memorize everything in a single vector all the time. Kind of our final big idea is maybe we don't even need to navigate information that's not even worth recording. The idea is there might be some parts of our input that we don't ever need to process. So the idea here is you're going to attend to a certain part of the image and only process that part that you've attended to and ignore everything else. So I really like this example. I give a link to the paper in the slide. What you're trying to do is predict what the speed limit is, and you see this image. And I don't know if you can tell. So this little circle here is the speed limit sign. Yeah, so it's 70 miles per hour. But if you're using a standard deep learning model, it's going to have to process this entire image just to figure out that it's 70 miles an hour. What you really should be doing is focusing, you should be like cropping out this part of the image and only processing that part. Right. So we're going to talk about how do you actually do this. The model that I'm going to talk about now is called the recurrent attention model. There are many ways to do hard attention, but this is one. The high-level idea is we need to figure out where to crop in our original image. We need to figure out a good representation of those cropped pieces. And then from that, the representation of these cropped pieces, I need to classify what the actual digit is, right? So we'll just solve each piece one at a time. So, well, actually, we will skip the question of how to crop or where to crop, and we're going to just think first, if you had a crop, how would you summarize it? This part's actually a little bit easier, right? Idea is not too complicated. Say we have this location that we want to crop. What we would do is we take a few images of different sizes around that position. So they call this foveal attention in the paper, but in my mind it's just crops of different sizes that have been resized to the same shape. And then we just encode it. I think it's just an MLP in the paper, right? So a one-layer thing. And then you also encode the raw location coordinates, like a two-dimensional XY coordinate. You encode all these using an MLP, you get some vector, right? This is your encoding of that crop. Okay, now how do you classify? The point is, we have encodings for each of these different crops. So this picture should remind you of something. It should look like you have a sequence of summaries, and you want to turn that sequence of summaries into a classification, right? So that should make you think of an RNN. And that's exactly what people do, right? You treat each of these encodings as inputs. These are like the XTs now. And I have a running summary of all those inputs. The running summary is telling you where have you seen, like what have you looked at so far across the entire image. And then from that final encoding, you're going to classify what the digit is. You might ask, why not just concatenate all the encodings and make the prediction? And honestly, I think that would probably work. But the motivation in this paper, if you do it this way, you can kind of take as many crops as you want. And you just sequentially update that number of crops, put these into the same dimensional summary as a fixed thing, you can classify. Okay, and we've kind of, in the process of thinking through this how do we crop things, we've almost come up with an answer for where you should crop. Right? The idea is going to be, use the encodings you have so far to predict the place that you should be cropping. Right? So think of it as like you now have both a end of the sequence supervision and a kind of within the sequence per input supervision as well. Right? So that's it, right? Like we now have a piece to crop. We know where to crop. We know how to summarize our crops, and then we can finally use that final encoding to classify. But there's a small detail. We're so close, but not quite there. The issue is, it's the way that they propose in this paper is you shouldn't crop things in a deterministic way, right? You might imagine like we could just predict the location to crop and then just use that and everything will be fine. But instead what they say is you want your future crop to be kind of random. even if you've had a fixed set of crops that you've seen so far, you want the next place that you look to be kind of a random crop around some general area, right? So what I'm showing here is you kind of predict the center point, but then the actual crop you get is going to be some random value around that center point, right? This apparently makes things more robust, right? But it makes training more complicated. You can no longer just backprop through everything because there's an element of randomness. Backpropagation only works when you have a deterministic function. So, a little bit more precisely, kind of what we are used to is we have a deterministic function of some parameters, and then we're just trying to minimize that. What we have instead is we see the random locations that are centered around some fixed parameter, and we want to minimize some function, some loss, across all these draws. Right? So how do we pick a parameter that when you randomly sample many of these draws, the loss will be small? That's the question. To get something of an answer, we're going to try to review a little bit of gradient descent and then see what needs to be changed. Right? The nice thing is, kind of even before this paper, a long time before this paper, this sort of optimization problem had been considered before. So it's not like they had to make up both this hard attention model and the way for training. It's just they use this kind of classical way for training. I think if you do the RL practical, they'll discuss this in a little bit more detail too. But the picture. So how does gradient descent work? The usual idea is, well, we need to be able to take this parameter mu, we evaluate the function at that mu, we evaluate the gradient at that mu, and then we now update to a new value, right? So we needed two things. We needed the value of the function at that parameter, and we needed the value of the gradient at that parameter. Once we had that, we had everything we needed to just march along to get to the minimum of the function. Now, what breaks when we try to do our random approach? Everything breaks when you try to do the random approach. So first of all, we have a value mu, which determines this kind of distribution around which we sample the crops, but we don't observe the function at mu, right? We observe it at the random crops that are kind of around mu. And then second of all, you can forget about gradients. We don't even have f of mu. How will we have gradient of f at mu? So we can't do gradient descent. But what would you do? Let's say we actually observed observations like this, and your goal was find mu that minimizes this function. The natural thing to do would be you look at where the function is smaller, and you just move mu towards where that function seems smaller, right? So that's what this picture is, right? Now I see the updated function. I can now get samples from it. And I think okay, it's still a little bit smaller here. It's not that much smaller, so it won't move too much. But you would still kind of move in this direction. And you would do this a few times until you get near the bottom. And that's actually exactly what this identity is telling you. So what in my left-hand side, I'm trying to differentiate this thing that I want to minimize. Right-hand side, you can figure out this identity not too hard. It's just differentiating under the integral. But I'd rather try to interpret the final thing. And a hint for people who are afraid of formulas. If you see something that seems scary, always try to break it into the smaller pieces and then understand what each of the pieces does and then kind of put it all back together. So we'll do an exercise. We have a summation f of L and then L minus mu, right? Let's pretend all the f's were equal to each other, right? So if it's kind of constant flat samples, then what is this? This is just some LTI minus mu. Since the LTIs are all centered around mu, this should be about 0, right? Which makes sense. If all my evaluations were kind of constant, then I don't try to move my parameter in any direction. It's kind of a local optimum, right? But now what happens if some of the f's are much larger than others, right? If some of the f's are much larger than others, then I move in the direction more towards that L, right? So that L is kind of upweighted, kind of up-prioritized, and I move my new update towards that L, right? So, I mean, that's going to do a kind of ascent, right? But then now we just flip the sign, and now we can do descent, right? So you just do the negative of the gradient. This is just the gradient. So that's reinforce. And here's another picture. So this is what it starts with. And I see the value of the function, and I'm just doing this exact picture that I had walked through. And eventually it kind of converges, and it knows that it's not going to move much. Okay, so hard attention, just putting it together, we needed modules that learned to crop and summarize, and we needed a training mechanism that knew how to deal with randomness. Once we can put these two together, you can kind of train end-to-end something that crops relevant information, summarizes, and predicts, right? And the real point I want you to remember is kind of, we've made a little bit of a trade-off. We have a much more complicated training procedure for one. But we now can avoid processing huge parts of images and input data that are not actually that relevant. So you trade off a little bit of kind of mathematical training complexity in favor of kind of huge computational benefit. And that's the end of part one. Main takeaways: compression is important for good models, navigation is important, gating can help us avoid vanishing gradients, soft attention helps us with this navigation problem, and hard attention keeps us from having to process lots of irrelevant information. Any question?
Yeah, I've got two simple questions about the drop in sound. How's the initial drop chosen?
It's chosen at random. I think that's, yeah.
What's the mean?
The mean? I'm not sure. I think it might be you have to have like some random pre-first crop point. And then once you have that, you pass through forward, and that first pass through the RNN becomes where you crop. I think that's probably how you do it.
The second question I've got, we have drops of different sizes.
Oh, yeah.
How do I transform them into the same pixel?
Oh, yeah. So you just, you like upscale, right? Yeah. Any question?
How can I apply hard attention to text data that require sequences?
I mean, I'm not familiar with papers that do this, but this sounds like something that I'm sure someone has done. In theory, it seems like you should be able to take like a very large paragraph and then figure out the parts of the paragraph that might be relevant for whatever classification you have, right? But then the actual kind of cropping and training procedure, you might have to design yourself. You would probably have to have your own modules that know how to summarize that phrase. But you know, if you find some papers, you should let me know. Okay, and I guess next, all the references here. And next, Aidan is going to tell us about some of the more state-of-the-art modules, kind of the things that people are using in practice.